Alright folks, this video will be on orthonormal sets. I'm assuming you have a basic understanding of the dot product, the norm of a vector, how to tell if two vectors are orthogonal, and what the definition of a unit vector is. By the end of this vector, you should be able to determine if a set is orthonormal and determine if a matrix is orthogonal. So the first thing that I want to do is define an orthonormal set. A set S of indexed vectors is called orthonormal if it's an orthogonal set of unit vectors. Remember that orthogonal vectors are automatically linearly independent, and so if W is the span of this set, then S is called an orthonormal basis for W. So there are two things to check here when I'm trying to check if something's an orthonormal set. And I just remember these by looking at the words ortho and normal, splitting this apart. Ortho refers to orthogonality. So that means that these vectors are orthogonal. In other words, ui dot uj is equal to 0 for every pair of vectors in this set. So I have to check pair by pair every combination of vectors. The word normal tells me that each of these is a unit vector. And so for this, I just need to check for every ui that the norm of ui is 1. It's usually easier to check if the set is normal, checking that everything is a unit vector, because if I find out that one of these is not, then I automatically know that this is not an orthonormal set. So in this first example, I just want to check that the set is orthonormal. So here's a set B of vectors, and I want to check that it's orthonormal. So I'm going to start again by checking whether or not the vectors are unit vectors, because this is an easier thing to check, and if it fails, then I'm done. So B1, the norm of B1 is going to be the square root of each entry squared. So the first entry squared is 9 over 11. Second entry squared is 1 over 11. Finally, plus 1 over 11. And so 9 plus 1 plus 1 is the square root of 11 over 11. This is just the square root of 1, which is 1. In fact, if I'm actually trying to check if something's a unit vector, I don't even need to take the square root, because the square root of 1 is always 1. I just need to check that the actual sum of the squares is 1. I'm going to keep checking that the norm is 1, but maybe just a trick. So the norm of B2 is the square root of negative 1 over square root 6 squared, which is 1 over 6, plus 4 over 6, plus 1 over 6, the square root of that. This is equal to the square root of 6 over 6, which again is the square root of 1, which is 1. Finally, the norm of B3 is equal to 1 over 66 plus 16 over 66 plus 49 over 66. The square root of that is the square root of 1, which is equal to 1. And so that implies that this set is normal. Every vector is a unit vector. So that's the first step in checking out whether or not this thing is orthonormal. So the next thing that I want to check is whether or not the vectors are orthogonal to each other. So for each of these, I'm going to take a dot product of v1.v2, v2.v3, and v1.v3. Now remember, v1.v2 is the same thing as v2.v1, so I actually only need to check 3 pairs instead of 6. So, for example, v1.v2, this is going to be 3 over root 11, 1 over root 11, 1 over root 11, dotted with negative 1 over root 6, 2 over root 6, 1 over root 6. So this will be negative 3 over root 6 times root 11. That's root 66, but some of these are going to get kind of big, and it actually won't matter because the denominators would all be the same. This is plus 2 over root 6 times root 11, plus 1 over root 6 times root 11. And so that's negative 3 plus 2 plus 1. All the denominators are the same, so this is 0 over root 6 root 11, which is just 0. v2.v3 will be negative 1 over root 6, 2 over root 6, 1 over root 6, dot negative 1 over root 66, negative 4 over root 66, and 7 over root 66. And so this will be negative 1 times 1 is 1 over root 6 times root 66, minus 4 times 2 is 8 over root 6 times root 66, and finally plus 7 over root 6 times root 66. Again, all the denominators are the same. 1 minus 8 plus 7 is 0. And so these two vectors are orthogonal. And finally, the last pair of vectors I need to check is v1 dot v3. v1 dot v3 is 3 over root 11, 1 over root 11, 1 over root 11, dotted with negative 1 over root 66, negative 4 over root 66, 7 over root 66. And so again, I'm not going to worry about the denominators here. They're all going to be the same, root 11 times root 66. So this is negative 1 times 3 is negative 3 over root 11 times root 66 plus, or rather minus 4 over root 11 times root 66. Finally, plus 7 over root 11 times root 66. Again, all the denominators are the same. I can add right across the top. Negative 3 minus 4 plus 7 is equal to 0. And so that means that all of these are orthogonal. So I know that all of my vectors are orthogonal. They all have unit length. And so that means this whole set is orthonormal. In fact, it's an orthonormal basis for R3 because there are 3 vectors spanning all of R3. Okay, so I want to now give you a definition and a theorem. So an m by n matrix U has orthogonal columns if and only if U transpose times U is equal to I. So this is really very useful. It's a useful property of the transpose. I can take a set that I'm trying to determine if is orthonormal, and I can put it in a matrix and check if U transpose times U is equal to I. That will tell me that the vectors are orthonormal and that the vectors form some sort of basis for the set they span. A definition for you, an invertible matrix with orthonormal columns is called an orthogonal matrix. Orthogonal matrix have a nice property that U inverse is equal to U transpose. So I want to use now this theorem in an example. I want to check that this matrix has orthonormal columns. I could certainly check that each column is a unit vector and that their dot product is equal to 0. There's only 2 vectors here. That wouldn't take too long. But I want to use this new theorem that I have, which tells me that if ut times u is equal to I, then that means that my matrix has orthonormal columns. You'll find out actually in this example, and I'll show you why, that this isn't harder, it isn't easier than actually checking whether or not they're unit vectors and whether or not their dot product is 0. It's just a nicer way to organize my work. So let me show you. U transpose is 1 over root 2, 2/3, 1 over root 2, negative 2/3, and 0, 1/3. I want to multiply that by U, which is 1 over root 2, 2/3, 1 over root 2, negative 2/3, 0, 1/3. And so entry by entry, 1 over root 2 times 1 over root 2 is 1/2. Again, 1 over root 2 times 1 over root 2 is 1/2, and 0 times 1/3 is 0. In the next entry, I have 1 over root 2 times 2/3. This is 2 over 3 roots of 2, minus 2 over 3 roots of 2, plus 0. In this next entry, I'll have 2/3 times 1 over root 2 again. This will be 2 over 3 square roots of 2, minus 2 over 3 square roots of 2, plus 0. And finally, in this last entry, I have 2/3 times 2/3, which is 4/9, plus 4/9, plus 1/9. And so this is certainly 1, 0, 0, 1. So I want to show you something really nice. It's not a coincidence that the upper right entry and the lower left entry are the same. It actually has to do with the fact that when I multiply this matrix, what happens is this first entry here is literally U1, the norm. So I found out that the norm of u1 is 1. In this bottom right entry, this is literally the norm of u2. How do I find this entry? I multiply the bottom row times the second column of the transpose and u. So that gives me the norm of u. This entry here is actually the first row of my transpose times the second column of u itself, which is literally the dot product of u and u2. And so this is equal to 0. And this is the dot product of u2 dot u1. So I'm actually doing all the same work here. I'm just packaging it differently. I'm just organizing it differently in a much nicer, more organized way. The last theorem that I want to give you talks about U with orthonormal columns. So if U is an m by n matrix with orthonormal columns and x and y are elements in Rn, then the norm of ux is equal to the norm of x. So this is very useful if I know that U is a standard matrix for a matrix transformation, or if U is the standard matrix for a transformation that's associated to a transformation between two finite dimensional vector spaces. I also have that ux dot uy is x dot y. So this shows us that ux is perpendicular to uy if and only if x is perpendicular to y. So this is very useful again. If I have transformations, it sends perpendicular vectors to perpendicular vectors. And finally, ux dot uy is equal to 0 if and only if x dot y is equal to 0. So these are all very useful properties if I know that U is the transformation, some matrix transformation from Rn to Rm. Okay, I want to check now, I want to verify the first property in this theorem. I'm going to do it with the example we've already looked at. So let U be the matrix in the previous example, and x be this new vector, root 2, 3. I want to verify that the norm of x is equal to the norm of u times x. So first I'll check the norm of x. The norm of x will be root 2 squared plus 3 squared under a square root. So this is 2 plus 9 square root. This is the square root of 11. So I want to check now that the norm of u times x is equal to square root 11. So first I'll multiply and then I'll take a norm. 1 over root 2, 2/3, 1 over root 2, negative 2/3, 0, 1/3, times root 2, 3. So this is going to give me a vector in R3 that looks like this. 1 over root 2 times root 2 is 1, plus 2/3 times 3 is 2. 1 over root 2 times root 2 again is 1. This time minus 2/3 times 3 is minus 2. And finally 0 times root 2 is 0. 1/3 times 3 is 1. And so this vector is 3, negative 1, 1. So let's check its norm. The norm of 3, negative 1, 1 is equal to the square root of 3 squared plus 1 squared plus 1 squared. And so this is, again, 9 plus 1 plus 1, and so that's the square root of 11. And so you see that U, if it was a transformation, a matrix transformation from R2 to R3, it doesn't change the norm of a vector. Okay, in this last example, I just want to show you how to determine if something's an orthogonal matrix. We're actually not going to do any work here. We've already seen this example. We looked at these vectors, the columns of U independently, and verified that they made an orthonormal set. And so this is an orthogonal matrix because it's a square matrix with orthonormal vectors. So there is actually one thing to check here. Remember that orthogonal matrix, I'm just going to state the definition again. Orthogonal matrix, if and only if U is invertible, and has orthonormal columns. So we know that the columns are orthonormal. We know this because of a previous example that we did. So they're orthonormal. So that means, actually, since they're orthogonal, this means that the columns are linearly independent. And by the invertible matrix theorem, this tells us that because the columns are linearly independent, U is invertible. And so since U is a square matrix, it's invertible, it has orthonormal columns, this means that U is an orthogonal matrix. Okay, so that's all I have for you today. Again, we learned what an orthonormal set is, what an orthogonal matrix is, and how to work with these definitions and check them. I hope you enjoyed this video. I hope you got something out of it, and I'll see you next time.